If a equals g of b equals log base 2 of b, find b equals g inverse of a. I'm going to start with my log equation, a equals log base 2 of b. I need to solve this equation for b. I can do so by switching this from log form to exponential form. The base of my logarithm is 2, so the base of my exponential is 2. Remember, the logarithm is always equal to the exponent, so my exponent in this case is a. 2 to the a equals b. So b equals g inverse of a, which equals 2 to the a. We can verify that these two functions are really inverses of one another graphically. So let's pull up our graphing calculator. In the y equals menu, I'm going to plot the logarithm first. Remember, I always have to write y as a function of x on the graphing calculator. So instead of a and b, I'm going to be using y and x. Y equals log base 2 of x. Also remember that our calculator doesn't have base 2 logarithms. I can easily use the change of base formula to change log base 2 of x to a natural logarithm. Log base 2 of x equals natural log of x divided by natural log of 2. Let's plot that. Natural log of x divided by natural log of 2. In y2, I'm going to place my exponential function, in this case 2 to the x. And I'm going to plot y3 equals x because inverse functions are reflections about the line y equals x. Let's graph all three. Note my line diagonally up the center here is y equals x. The exponential function lies above the line. The logarithmic function lies below the line. Let's look at some points on these graphs. So starting with our first graph, the logarithm, let's choose an input, which is a power of 2, because we're working with a base 2 logarithm. Let's just start with 2. With an x-coordinate of 2, our y-coordinate is 1. The point 2, 1 is on the graph of the logarithm. This makes sense. Put in 2 for our input of the logarithm. 2 raised to what power gives me 2? Well, 2 to the first, of course, so my output should be 1. If 2, 1 is on the logarithm, then the point 1, 2 should be on the exponential. Remember, I entered the exponential function in y2, so we're looking for our second graph. There's the third one, that was the line. There's the second one. We're looking for this 2 in the upper right-hand corner here. So now I want to put in an x-coordinate of 1. When I do that, my y-coordinate is 2, just what we wanted. 2, 1 was the point on the log graph, so 1, 2 is the point on the exponential graph. And looking at our formula, that makes sense. If we input a 1, 2 to the first power is indeed 2. Let's look at one more example. 1/2 is another power of 2. Let's go back to our first graph, the logarithm, and put in 1/2 for x. The y-coordinate is -1. So if we put in 1/2 as our input in our log function, we're saying 2 raised to what power gives me 1/2? Well, 2 to the -1 is 1/2, so this makes sense. So 1/2, -1, is the point on the log function. We would expect -1, 1/2 to be the point on the exponential. So on the exponential graph, I want to have an x-coordinate of -1 and see what the y-coordinate is. So the exponential is graph 2. If I put in -1 for x, my y-coordinate is indeed 1/2 as expected. And again, this makes sense. If we input -1, 2 to the -1 is indeed 1/2. So it looks like graphically we see that we do have exponential and log functions here, which are inverses of one another. Base 2 logarithm, base 2 exponential. This makes sense.